Today we'll be talking about buffers. Buffers in chemistry. Now, one way we can make a buffer is by taking a weak acid or base, and then adding a salt, and adding a salt that contains a common ion with the weak acid or base. So common ion. So an example of this would be if we started off with 0.5 molar of HC2H3O2, namely acetic acid. And we added to this solution of acetic acid, we added, for example, 0.1 molar of a salt, namely sodium acetate, NaC2H3O2. And here what we find is that our common ion is going to be the acetate ion. So because from here, we have H plus and C2H3O2 minus, which is our acetate ion. And here we have our Na plus, which comes from NaOH perhaps. And we have C2H3O2 minus, once again, and this is our common ion. So we have our common ion here. Now, if we have this buffer, then we want to calculate the pH, its initial pH of our buffer. So we can use the Henderson-Hasselbalch equation, which says that pH is equal to pKa plus the base 10 log of the concentration of the base over the concentration of the acid. So this is called the Henderson-Hasselbalch equation. Now in our case, we need to figure out which one is the base and which one is the acid. Well, what we can begin with is what we have here, because we're starting off with our weak acid or base, and that's the one that's going to play an important role. When we're adding the salt, the only thing it provides is a non-zero initial concentration for our common ion, the common ion effect. So namely, we can write that acetic acid, HC2H3O2, is going to dissociate, or we can also think in terms of that it reacts with water. So I'll write that first. It reacts with water, and water gains the extra H plus ion. So what we find is that water becomes the hydronium ion, which we can also consider to be sort of an H plus, and we are left with the acetate ion as a product. So another way we can write this is HC2H3O2, and it's going to dissociate into H plus C2H3O2 minus, our acetate ion. Now the important thing to remember when we're writing it this way, however, is that the acetic acid is a weak acid. So initially, when we just have this solution, what it means to be a weak acid is that the majority of our acetic acid is going to remain that way, and it's not going to dissociate a lot to produce that many H pluses. So as a result, the pH isn't going to be very low or very acidic, in other words. So here we have that we know that this is going to be the acid. It's called acetic acid. And it's going to give up one of its H plus ions to water. So we also find that the acid is going to have a conjugate base, which means that from the acid we have a conjugate base as well as the H plus ion. And the conjugate base is basically just not the H plus. So once we have our conjugate base, then we can plug it into the Henderson-Hasselbalch equation. So we have pH is equal to pKa, which is just the negative base 10 log of the Ka value, which in our case for acetic acid is going to be 1.76 times 10 to the negative 5, and we're given that perhaps in an equation, plus we're going to have the log of the concentration of the base. In this case, it's going to be our conjugate base, and that's where our common ion effect comes in play. So we start off with 0.1 molar of our acetate ion, and that's because when we have the salt in our solution, it's going to dissociate into Na+ and our acetate ion. And so we start off with 0.1 molar of our ion. This is actually a little redundant since this implies molarity, but that's what we have. And then we have the acid is just going to be our initial concentration of our acetic acid, and what we find is that's just going to be 0.5 molar. And now what happens when we plug it in is that we should get the negative log of 1.76 times 10 to the negative 5 plus the log of 0.1 divided by 0.5, and that gives us a pH of 4.06. So we can conclude that for our example case, our pH is going to be 4.06, and that is the pH of our buffer.